Thank you. Thank you, everyone. Good morning, everyone. I'm Linghan Zhang from Florida State University. Today, I'm here to talk about our recent work, VoiceGesture, a liveness detection system for voice authentication on mobile devices. This is a joint work with my colleague Sheng Han and my advisor, Jie Yang. Well, let's begin with some background information. Biometric has gained extensive attention and importance since it's a promising alternative to legacy password. And among all the biometrics, such as face, iris, and fingerprint, voice has wide applicability since it's a primary way of communication, which enables voice samples to be acquired remotely through existing landline, cellular, and VoIP communication channels. Further, voice authentication has the advantage of natural integration with other authentication methods, such as password and face authentication on mobile devices for multi-factor authentication. Over recent years, voice authentication has matured to become a low-cost and reliable authentication method for a wide range of applications, such as access control forensics, law enforcement, and especially with the advances of mobile technologies, it has been widely adopted by a range of mobile applications. Examples like Google's Trusted Voice have integrated voice authentication with smartphone operating systems to provide secure access to Android devices. And applications such as Tencent's WeChat provide voice-based app login. Voice authentication has also been used for e-commerce and mobile banking. For example, financial institutions such as SHBC, CITI, US Bank have all started testing or are deploying voice authentication on their mobile applications or ATMs to allow their customers to bank without password and card swipe. Evidence shows that the predicted market of voice authentication will be over 180 billion in 2021. However, a growing body of research has claimed the vulnerability of voice authentication to systems to replay attacks, where an adversary tries to spoof a voice authentication system by using a pre-recorded voice sample collected from the genuine user. Well, replay attacks are easy to carry out, since it requires neither sophisticated equipment nor specific expertise, and the wide availability of high-quality digital devices makes them even more practical. And besides, an attacker could easily collect the victim's voice sample from his public conversation, or public speech, or just download from popular social media. Unfortunately, such a low-cost and low-effort attack have been proved to be highly effective in spoofing voice authentication systems. A study shows that replay attacks could increase the error rate of state-of-the-art voice authentication systems to around 30%. Well, to defend replay attacks, the previous methods mainly rely on the acoustic characteristics of the input signal. These methods, however, are less effective since a voice sample recorded with high-quality recorder under benign acoustic environment will be indistinguishable from the genuine one. And the voice authentication service providers mainly rely on challenge response methods. For example, they may ask the users to repeat a prompted message from their system except for the enrolled one. These methods, however, require additional user cooperation. And more recently, some smartphone-based voice authentication systems, liveness detection systems, have been developed. For example, some propose to sense the magnetic field emitted from the loudspeaker to defend replay attacks, while we propose to measure the time difference of arrival changes of a sequence of phonemes, which are the smallest units of a language, to the two microphones of the phone to detect a live user. Well, these methods are cumbersome because they either require the user to conduct some predefined manners or change their habitual way of speaking by requiring the user to hold their smartphone at a specific location. And to resolve these problems, we propose VoiceGesture. VoiceGesture allows the user to keep their habitual way of speaking, and the users could choose to hold their phone by their ear or in front of the mouth. And VoiceGesture is transparent to the users because it doesn't require any additional cooperations except for the standard voice authentication procedures. And importantly, VoiceGesture is highly effective compared with traditional methods? Well, we build VoiceGesture on text-dependent voice authentication systems, where user-chosen or system-prompted passphrase is used for authentication. This figure shows a typical text-dependent voice authentication system. We consider two types of attacks, playback attack and mimicry attacks. To conduct a playback attack, the attacker uses a pre-recorded voice sample collected from the genuine user to attack the system. And to conduct the mimicry attack, the attacker uses a far-field loudspeaker to play back the pre-recorded voice sample of the genuine user, and meanwhile, mimic the articulatory gestures of the genuine user. Well, the basic idea of voice gesture lies in the fact that when human speech, there are multiple articulators conduct multiple articulatory gestures. These articulatory gestures are multidimensional movements which allow us to distinguish loudspeakers from live users. And the diversity of human vocal tracts and articulatory gestures is adequate to discern different people. To capture these articulatory gestures, we use our smartphone as a Doppler reader. Specifically, the speaker will emit an inaudible sound at 20 kHz once the voice authentication is triggered. This signal will be reflected by the moving articulators and result in Doppler shifts. These Doppler shifts, and as well as the voice passphrase, will be recorded by the microphone. We extract user-specific frequency shift features for liveness detection. Well, let's take a closer look at articulatory gestures. Well, an articulatory gesture is actually a constriction of an articulator. And here are some examples of articulatory gestures, including lip protrusion, tongue constriction, jaw angle changes. Our articulator conducts precise and highly coordinated articulatory gestures. Well, for example, to pronounce the consonant P, most speakers need to move both their upper lip and lower lip, and meanwhile change their jaw angle. Moreover, different moving speed and intensity of the same articulatory gestures will result in different sounds. For example, to pronounce T, Z, a speaker needs to use the same articulatory gestures. However, these articulatory gestures are different in terms of their radial and angular. Well, these characteristic articulatory gestures actually could result in particular Doppler shifts, showing the following features. Firstly, the articulatory gestures will result in signed Doppler shifts. For example, an articulator moving towards the microphones will result in positive Doppler shift. And the faster articulatory gestures will result in larger Doppler shifts. So we could use the magnitude of the Doppler shift to distinguish different articulatory gestures. And thirdly, the reflections of closer articulator are stronger. We could use this information to differentiate different articulators. Well, we use 20 kHz sine wave as our prop signal since it's inaudible to a human ear, and such high frequency could maximize the Doppler shift. Well, unlike human, loudspeakers only move in one dimension to produce sounds. Specifically, when alternating electricity flows through the voice coil, it triggers a varying electric field to work with the standing magnetic field provided by the permanent magnet. This magnetic field then will attract or repel the voice coil and the attached diaphragm to move backward and forward to produce sound. The movement of the diaphragm is controlled by the input signal. Higher pitch and larger volume of the input signal will result in faster and harder pushes of the diaphragm. Although the diaphragm of the electrostatic loudspeakers are driven by status, they still rely on the one-dimensional movement of the diaphragm to produce sound. Here is an example showing the Doppler shifts of a live user and the loudspeaker when they produce the same sound. Well, in this figure, the x-axis represents the time, y-axis is the frequency, and the unshaded areas are the corresponding phonemes. As we could observe, the Doppler shift of the loudspeaker is much cleaner because it only represents the simple one-dimensional movement of the diaphragm, whereas the Doppler shifts of the live user looks more complex due to the complicated articulatory gestures. For example, if a speaker wants to pronounce the first phoneme, first he needs to open his mouth vertically and then gradually change to horizontal direction. This procedure involves extensive articulatory gestures and resulting massive Doppler shifts, which could not be observed in the diaphragm in the spectrogram of the loudspeaker. Well, we leverage this phenomenon to defend replay attacks. To defend mimicry attacks, we study the minute differences in the articulatory gestures among people when they pronounce the same phoneme. These differences could be caused by the physiological differences of their vocal tracts. Well, for example, the sizes and shapes of these three speakers' vocal tracts are quite different. Or people could choose different trajectories of articulators to pronounce the same phoneme. Well, for these three speakers, even when they are pronouncing the same phoneme, we can observe that their tongue body position and tongue body shapes and tongue tip positions are quite different. Moreover, people could also choose different articulatory strategies. For example, some speakers' jaw movements are closely connected with their tongue body movements, while some are not. These differences could be reflected by the moving speeds of their articulators. This figure shows the moving speeds of both the upper lip and the jaw movements of 5 different speakers. We could observe a diverse range of velocities. And fortunately, with 20 kilohertz, we actually could able to sense these individual diversities for liveness detection. Well, here we present the approach overview of our system. First, the built-in speaker emits an inaudible sound at 20 kilohertz once the voice authentication system is triggered. When the user speaks a passphrase, the built-in microphone records both the frequency shifts and the voice samples. Once finished recording, the voice samples, which are usually under 10 kilohertz, will be separated for conventional voice authentication, whereas the frequency shifts around 20 kilohertz will be separated for feature extraction. Our system extracts features based on both frequency shift distribution and energy distribution of the spectrogram showing Doppler shifts. These features then will be compared with the ones obtained from user enrollment. Well, to implement these procedures, we adopt this system flow. Generally speaking, we use Doppler shift extraction to extract Doppler shifts from the voice samples, and then we use feature extraction to extract features from these voice samples. These features then go through Wavelet-based Denoising to delete the noises, and the filtered features will be compared with the user profile for similarity comparison. Let's go to the details of each step. Well, specifically, once finished recording, we convert voice samples from time domain to frequency domain by using short-time Fourier transform for conventional voice authentication. We then conduct phoneme segmentation by using automatic speech recognition and MAUs. The result of this step will be labeled phonemes and their time steps. We then match these time steps to 20 kilohertz to extract the corresponding Doppler shifts. This figure shows an example of the result of this step. We could observe the phonemes and their corresponding Doppler shifts. We extract two types of features. The energy band frequency feature quantifies the relative speeds of the articulators. Specifically, we separate the energy into 3 levels and 6 subbands, among which the subband 5 and 6 show the movements dominated by the closest articulators, and the subband 1 and 2 are dominated by the motions of the farthest articulators. From each subband, we use the centroid frequency as the feature. We combine the centroid frequency of each phoneme to become a frequency contour of each band. The second type of feature we extract is the frequency band energy feature that measures the relative positions of articulators. We divide the frequency shifts into 5 subbands. Subband 3 reveals the energy of the slowest articulators, whereas subband 1 and 5 show the energy of the shows the energy of articulators with farthest movements. We could notice that subband 3 has highest energy level. It could be affected by the lower facial parts, which are close to the microphones, however move slowly. And by contrast, in subband 1 and 5, the furthest articulators, like the tongue, result in low energy. Nevertheless, tongue could be the most flexible articulators and thus provide considerable Doppler shifts. Our system used discrete wavelet transform to remove the mixed noises from the extracted features. Specifically, it decomposes the input signal into approximation coefficients and detailed coefficients. The approximation coefficients depict the trend of the signal, and the detailed coefficients contain the small-scale characteristic and the mixed noises of the signal. After 3 levels of decomposition, we apply a dynamic threshold to the detailed coefficients to remove the mixed noises while retaining the useful details. After that, we combine the original approximation coefficients with the filtered detailed coefficients and use inverse DWT to reconstruct the denoised contour. We use Pearson correlation coefficient to measure the linear similarity between the contour generated from the previous steps and the one stored in the user profile. The resulted coefficient ranges from -1 to +1. A value close to +1 indicates high level of similarity, while a value close to 0 implies a lack of similarity. Given the correlation coefficient of all contours, we use the average coefficient to compare with the predefined threshold to make the final liveness detection decision. Well, we employ 3 types of phones to collect the voice samples. These phones are always different sizes and audio chipsets. All of them are installed with Android 6.0 Marshmallow. They all support 192 kHz sampling frequency, and they are all able to provide 20 kHz audio playback and record. We consider 2 types of phone placement, as I mentioned. Put the phone by the ear or put the phone in front of the mouth. We collect data from 21 participants, including both males and females, native speakers and non-native speakers. We collect 100 positive cases from each of them, which adds up to 2,100 positive cases. We conduct our replay attacks with 3 different kinds of loudspeakers, including a Dell AC411 standalone loudspeaker, a built-in loudspeaker of Note 5, and a common Samsung earbud. While we kept the replayed audios are all collected with the same phone used for authentication, we have included 1,000 playback attacks. For mimicry attacks, we first video the articulatory gestures of a participant during his voice authentication. We only record the lower facial part for privacy concern. And then we invite other participants to watch this video closely and try to mimic their articulatory gestures. Specifically, we will instruct them to mimic their speed of speak, the range and intensity of the articulatory gestures, and so on. These participants will then conduct mimicry attacks in front of the legitimate smartphone when they claim that they are ready. We have collected 600 mimicry attacks in total. Well, here are some results of our experiments. This figure depicts the overall accuracy and equal error rate of our method on the replay attacks. We could notice that with one feature, our system provides around 97% accuracy, and the combined feature achieves the best accuracy and equal error rate, which are over 99% and around 1% respectively. Well, this figure shows the accuracy and equal error rate of our system under mimicry attacks. With one feature, our system could obtain around 95% accuracy, and similarly, the combined feature achieved the best accuracy around 99% and equal error rate of around 1%. We also compare the performance of our system under different phone placements. In high level, the results show that our system works well under both placements and thus allow the users to keep their habitual way of speaking. In particular, when placing the phone to the ear, we have the best accuracy at around 99%. Well, the best accuracy for placing the phone in front of the mouth is slightly higher. This is due to the fact that placing the phone in front of the mouth can capture the movements of the tongue better since the microphone is directly facing the open mouth. Well, generally speaking, the contributions of our work can be summarized as follows. We show that we could use mobile devices to sense the articulatory gestures. We show that it is feasible to capture the minute differences in different people's articulatory gestures when they pronounce the same sound. We develop VoiceGesture to extract user-specific features from their articulatory gestures for liveness detection. And our experiments show that VoiceGesture is highly effective. Well, thank you. Any questions?
We have time for a few questions. So I ask if you have a question, please come to the microphone and state your name and affiliation and then question.
Hi, I'm Tzipora Halevi. I'm from Brooklyn College. So when you ran the experiment, you said you had 21 people, I believe. But, I mean, were they all saying the same thing? How did you create your data set? Can you give more details?
Excuse me?
How did you create your data set? I mean, did all the subjects in your experiment, were they asked to say the same thing? Did you compare them saying the same words or phrases? Was it in a controlled environment? I mean, in a quiet lab? Can you say more about this?
Well, thank you. Actually, we allow all the participants, they can choose their own passphrase. And each participant, they are allowed to choose 10 passphrases. This is all depends on themselves. And they can choose their own phone placements. But we do ask, like, all the participants, we will give them a same passphrase so we can compare the differences, the individual diversities.
So they did say the same passphrase?
Only one of them. 1 of 10, yeah.
1 of 10.
Yes.
So did you compare for the other ones? I mean, what's the impact of the fact that, I mean, you were trying to recognize it's the same person, right?
Yes.
So what's the impact of what they were saying versus the other features in the voice? The fact that each person was saying something else, what's the impact of that on detection?
Excuse me?
Well, if I say one thing and somebody else says another thing, you may be able to recognize, I mean, a machine may be able to recognize us either by the underlying feature of our voice or by what we are saying. How do you differentiate between these?
Yeah.
I think she's asking what happens if you have multiple users saying the same thing. How does your system differentiate between two users that are saying the same passphrase?
Well, as I mentioned, we leverage the individual diversity to differentiate them. Like even when they speak the same passphrase, because they have different physiological characteristics of their vocal tracts, or they might choose different articulatory movement trajectories, or they can choose different articulatory strategies. Yeah. So there are.
Do you have results for this case where everybody says the same thing?
Well, we did present that result in our paper, but I'm sorry it's not on my slides.
So what are the results? Can you summarize?
Well, actually, different people do show a lot of differences. As I remember, the results will be like around 99% to differentiate different people. Yeah.
Hi, David Coates, Dartmouth College. I had a question about your attack slides, your Mimicry Attack and your Playback Attack. I guess 2 questions. The metrics you used were accuracy and equal error rate.
Yes.
But for an attack, the attacker only cares about the false positive rate.
Uh-huh.
So I was wondering if you had broken out the false positive rate. Equal error rate kind of buries that in there with the other aspects of accuracy. What I really want to know in order to evaluate the effectiveness of a system in defending against an attack is the false positive rate. How often does the adversary succeed? And your plots don't really show that. So
okay. You mean the false accept rate?
Yes, same thing.
Oh, okay. Actually, well, I couldn't record the exact number for now, but
if it's not in the slides or the paper, maybe we can talk
yes,
about it. My other question is, in a mimicry attack, did your sample population all, for example, were they all native English speakers? Were they all native Mandarin speakers or something? Because the accent, for example, my accent is different than hers and is different than yours.
Yes.
And that itself is a very distinguishing feature. And it would make it difficult for me to mimic your voice. Also, our gender is different. Also, I'm sick. And so I'm wondering, you know, how did you control for those factors?
Well, actually, we have both native speakers and non-native speakers. And yes, you're right. If like the people, actually their articulatory gestures will be very different. If they have different accent or dialects, that affect this a lot.
In fact, you may not need articulatory gestures to distinguish speakers if one of them has a strong accent and the other does not, or different accents, right? And so I'm wondering how, in other words, you kind of need to control for that already differentiating factor. And it's difficult to do if you have a mixed population. So I'm curious how that affects your results.
Well, we didn't control that. We asked our participants to keep their habitual way of speaking, keep their own, like...
Even when they were mimicking.
When
their goal
mimicry
was to actually
attack.
mimic someone else.
Well, for a mimicry attack, as I said, we will record the articulatory gestures of the victim, and then we ask other participants to watch that video closely. They can watch this video like as many times as they want, and we will supervise that. If they claim that they are ready, and like I will supervise them. Like I will check if they are really ready or not.
Okay. Well,
yeah.
It's all I'm saying is that it's challenging, and it's something you should think about as you refine your results.
Thank you.
All right. We have time for maybe one more question. If you want to allow our next speaker, go ahead and start setting up. So here, go ahead.
Okay, so Max Hoffmann, Ruhr University, Bochum. And my question is basically, if I hold the phone to my mouth, to my ear, then the distance is basically the same for every human being. But if I hold it in front of my face, I can talk like this, I can talk like this. So does this influence the measurements? And
about the influence? Well, according to our experiments, when you hold the phone like within 2 centimeters away from your mouth, the accuracy of our system could still be 97%. But of course, you can't hold your phone like 20 centimeters away. That doesn't work. Due to the signal attenuation in the media. So if you hold the phone too far away, you probably can't collect any Doppler shifts.
So 2 centimeters are quite close, and I personally only telephone like this. So do you have any numbers on how people who usually use their phone like this, how far they hold it away? Because if I have to hold my phone closer, I also change the way I'm speaking, so I focus more on the way I articulate, and this already changes how I speak, right?
Well, actually, when you know you're doing voice authentication, you won't just hold the phone randomly anywhere. Most likely you'll hold the phone close, and also because the time you need to do a voice authentication is usually just 2 to 3 seconds. So we expect you don't move this phone in large scales.
Yeah. Okay, thank you.
Thank you.
Let's thank Linghan again.
Thank you.